Hello everyone, myself Dr. Meagle S. Matthew. Today we are going to see the first lecture of nanotechnology, that is Introduction to Nanomaterials. So in this lecture, we are going to see the definition of nanomaterials, origin of nanoscale materials, and how the nanoscale material is classified according to their dimension, and how the nanoscale material is generally synthesized. There are two strategies are there. One is top-down approach and another one is bottom-up approach. And a brief discussion about two important zero-dimensional nanomaterials, metal nanoparticle and metal nanoclusters, its properties, synthesis methods and applications. What is meant by nanoscale material? Nanoscale material is the material with at least one dimension is less than 100 nanometers. And a nanometer is a 1 billionth of a meter, that is 1 nanometer is equal to 10 raised to minus 9 meter, and it approximately 1 lakh times smaller than the diameter of a human hair. And the word nano derived from Greek word nanos, it means dwarf, and because of its extremely small size it shows unique optical, electrical and magnetic properties. These emergent properties have the potential for the great impact in electronics, medicine, optics and other fields. Here we can compare the size of the nanoparticle with the other biological systems. Since the nanometer scale is also interested in biological system, many proteins are tens of nanometer in size, and thus the nanostructures are easily incorporated into biological system due to their similar size scale. Coming to the origin of nanomaterials, one of the first scientific report is the synthesis of colloidal gold particle by Michael Faraday in 1857. Before that, the nanomaterials have been in use since ancient times. Since the 4th century of AD, the cup is named as Lycurgus cup. It is an extraordinary work with glass made by Roman glassworkers. It is considered as one of the greatest example of nanotechnology in the ancient world. It is having the image of King Lycurgus. Surprisingly, when the light irradiated from the outside of the cup, it looks green. When light irradiates from inside, the cup looks reddish and the King Lycurgus look purple. The explanation for this phenomenon was obtained only in 1919. After scientists analyzed the cup using an atomic force microscope, and it is found that the dichroism or the different color is observed due to the dispersion of metal nanoparticle, that is 66.2% silver, 31.2% of gold and 2.6% of copper in a glass matrix. The red color is observed as a result of absorption of light by the gold particle, and the purple result due to the absorption of larger particle, while the green color is observed due to the light scattering by colloidal dispersion of silver particle within the size of 40 nanometer. And the Lycurgus cup is recognized as one of the oldest synthetic nanocomposite. And the word of miniaturization was introduced by a great scientist, Richard Feynman, in 1959. He gave a talk called "There is a plenty of room at the bottom" at an annual meeting of American Physical Society at Caltech. In his famous lecture, Feynman laid the conceptual foundation for the field of now called nanotechnology when he imagined the day when the things could be miniaturized. Now we can see how the nanoscale material is classified according to their dimension. That is, it is classified as zero-dimensional nanomaterials, one-dimensional nanomaterials, two-dimensional and three-dimensional nanomaterials. What is meant by zero-dimensional nanomaterials? The zero-dimensional nanomaterials means the material having all dimensions should be less than 100 nanometer. That is spherical nanoparticle. Example, fullerene or gold nanoparticle, carbon dot, etc. Then one-dimensional nanomaterials are the material with one dimension is outside the nanoscale and two dimensions are in the nanoscale. Example for one-dimensional nanomaterials are nanotubes, nanorods, nanowires, etc. Then two-dimensional nanomaterials are the material with two dimension are outside the nanoscale and one dimension are in the nanoscale. Example for two-dimensional nanomaterials are plate-like materials such as graphene, nanofilm or nanolayers, etc. Then what is meant by three-dimensional nanomaterials? The three-dimensional nanomaterials are the material with they are not confined in the nanoscale in any dimension. That is, this class contain bulk powders or dispersion of nanoparticles, bundle of nanowires and nanotube as well as multi-nano layers. Then we can see how this nanoparticle is synthesized. As we already mentioned that the nanoparticle is synthesized by two common strategies. One is bottom-up approach and another one is top-down approach. Then what is meant by bottom-up approach? The bottom-up method where the atoms are assembled to generate nanostructures. In top-down method where the material is removed from the bulk material, leaving only the desired nanostructures. The common top-down techniques are photolithography and electron beam lithography. And the bottom-up technique include templating or chemical, electrochemical, sonochemical, thermal and photochemical reduction techniques. And the bottom-up synthesis technique usually employ an agent or a ligand to stop the growth of the particle at the nanoscale. And it is named as capping materials. The capping materials are the surfactant or polymers are used in this technique to prevent the aggregation and precipitation of the metal nanoparticle out of solution. And the choice of the reduction technique, the time and capping material are determines the size and shape of the nanoparticle generated. Usually, depending upon this choice of this ligand, the nanoparticle are in the shape of spheres, cubes, discs, wires, tubes, etc. And these are the few examples of zero-dimensional nanomaterials. And here we can see that the polymer nanoparticle are spherical in shape and micellar, liposome, dendrimers, gold nanoclusters, silica nanoparticle, iron oxide nanoparticle, gold nanoparticle, quantum dot. These are all spherical nanoparticle. That is, it is under the category of zero-dimensional nanomaterials. And in my presentation, I am mainly focusing on metal nanoparticle and metal nanoclusters. What is the major difference between these two nanoparticles? In the case of metal nanoparticle, for example, gold nanoparticle are the particle with the size in the range of 2 to 100 nanometer. And it possesses distinct physical and chemical properties like surface plasmon resonance, conductivity, surface functionalization, redox property, and these properties can make them excellent scaffold in the field of biomedicine like sensing, imaging, etc. And this nanoparticle can be synthesized in a straightforward manner and it can be made highly stable also. And it possesses unique optoelectronic properties and they provide high surface to volume ratio with excellent biocompatibility using appropriate ligand. And in another case, these properties of this nanoparticle can be readily tuned by varying their size or shape or surrounding chemical environment. And one of the major important property of this metal nanoparticle, for example gold nanoparticle, is the surface plasmon resonance of the nanoparticle. When the metal nanoparticle are exposed to a specific wavelength of light, the oscillating electromagnetic field of the light induces a collective coherent oscillation of the free electrons, which cause a charge separation with respect to the ionic lattice, forming a dipole oscillation along the direction of electric field of light. The amplitude of the oscillation reaches the maximum at a specific frequency called a surface plasmon resonance. Usually in the case of gold nanoparticle, the surface plasmon resonance is in the range of 520 nanometer. When the size of the gold nanoparticle changes from 10 nanometer to 50 nanometer, the maximum extension of the SPR band shifted from 517 to 532 nanometer in the visible region, which indicate that this intensity and absorption band of gold nanoparticle are concentration and particle size dependent. Generally, the spherical nanoparticle is commonly synthesized using a citrate reduction method reported by Turkvich. And in citrate reduction method, an aqueous solution of gold chloride is treated with the reducing agent citrate, which can produce nearly monodispersed gold nanospheres. And the size of the nanoparticle can be controlled by varying the citrate gold ratio also. And these nanoparticle can be formed. The nanoparticle can be characterized using various spectroscopic and microscopic methods. The spectroscopic methods like UV visible absorption spectroscopy, XPS, XRD, FTIR, etc. And the microscopic technique used to characterize the nanoparticles are transition electron microscopic technique, scanning electron microscopic technique, atomic force microscopic technique, and STM also. The SEM and TEM image will give an idea about the morphology as well as the size of the nanoparticle. SEM image will give the morphology of the nanoparticle and TEM image will give an idea about the exact size of the nanoparticle. And monodispersity of the particle also we can find using SEM and TEM image. And coming to the UV visible absorption spectrum of gold nanoparticle, here we can see the absorption maximum at 520 nanometer, that is around the nanoparticle is become a reddish color with a size in the range of 5 to 10 nanometer. When the size of the nanoparticle is increases, the UV surface plasmon resonance peak will shift to higher wavelength region. There is a red shift is observed and the color of the solution is also changes from red to purple with increase in the size of the nanoparticle. And FTIR spectroscopy also will give an idea about the stabilizing ligand used for the nanoparticle synthesis. And usually the FTIR spectroscopy usually will give an idea about the surface functional group present on the surface of the nanoparticle. And what are the changes of the functional group after binding on the surface of the nanoparticle also monitored using FTIR spectroscopy. And coming to noble metal quantum clusters. It is a sub-nanometer core-sized material made up of several tens of atoms. And the size of the nanoparticle is in the range of 1 to 2 nanometer. These are the major difference of the nanoparticle and the nanoclusters. Nanoclusters having the size in the range of 1 to 2 nanometer, whereas the nanoparticle is having the size in the range of 2 to 100 nanometer. And because of this extremely small size, it is considered as a missing link between atoms or molecules to larger sized nanoparticle. And the structure of the nanocluster is look like a core and shell like structure. Core is made up of metal-metal linkage and shell is coming from the various ligand used for the stabilization of the nanoclusters. These are the conventional ligands used for the stabilization of the nanoparticle, that is dendrimers or DNA, small thiol molecule, polymer, protein, etc. And because of this extremely small size of the nanoclusters, it possesses unique properties like luminescence in the visible to near infrared region, long lifetime, large stock shift, excellent biocompatibility, and fascinating photophysical and chemical properties, rich surface chemistry, etc. And one of the major difference between the nanoparticle and nanocluster is the nanocluster, almost all the nanoclusters are luminescent material, whereas the nanoparticles are non-luminescent. Because of the luminescent property, it can be exploited in various fields like biomedicine, optics, electronics, etc. And these are the major application of the noble metal quantum clusters in the field of energy, environment, and health. In the field of biomedicine, it can be used for the cancer therapy, drug delivery, or imaging, etc. In environmental field, it can be used for the detection of various explosive or the catalysis, and in the energy field nowadays these nanocluster are used for the development of photovoltaic devices. And these are all about the introduction to nanomaterials, and thank you for listening.